Welcome to the garden. Today we're going to be having a quick look at stepper polarity and whether or not stepper polarity actually matters. And the quick answer to this is yes. Now, we have this stepper motor wired up in such a way that we are energizing, or the code is energizing the coils in the way as wired here to spin clockwise here. And it just does one rotation, and then we're going to start changing some wires around and see what happens. So if I reset this stepper motor is going to do one rotation in the clockwise direction because we've wired it as said on the card and programmed it in the same way. So there's our one rotation in the clockwise direction as we expected. Now, what happens when you find an unknown stepper? Because if you haven't got this card, how do you know? Well, if you've got 4 wires, you've got 2 coils. And what you can do is say that this is one coil, and this is your other coil. And now we can measure the resistance between the pairs of wires. And if you measure between this wire and this wire, you're going to get infinite ohms, and the same from this wire to this wire, because they're not connected. But if you measure from this wire to this wire, you are going to get ohms, and sort of a typical value for this could be about 90 for an EEV. And obviously this coil here, you'll find the same thing. If you measure from either of these 2 cables to either of these 2, you're going to get infinite. So if you measure from there to there, you're going to get infinite ohms because there's no connection. Whereas again here, you're going to get 90 ohms, assuming it works fine. And then from that, you've now worked out which pairs, or which cable pairs are your coils. Other option, if you've got, say, a 5-wire stepper, which would be a unipolar stepper, you might have a tapping here and a tapping here as well. And this will be some common tapping that goes off. And now what happens, if you measure from here to any of these cables, whichever phase you measure, well, you're going to get 45 ohms, and you're going to get 45 ohms there as well. And here you're going to get 45 ohms, and here you're going to get 45 ohms. And that way, you know that it's common and it's in the middle of all of them. Whereas when you measure between the other direction, or the other wires on the other direction, you're not going to get infinite again, or 90. And from that, if you draw out a table, you can just work out which 2 are your pairs, which, for instance, on this stepper, is the black cable, and the blue cable, and the green cable, and the red cable. So what that means is that we can say that this is A plus, and this is A minus, and this is B plus, and this is B minus. But if we go back to here, what we can see is that when you look at this in step, what's a good step for this? Step 1, we'll say. B plus is positive and B minus is, well, not negative, it's ground at that point. So you've got voltage / current, conventional current, flowing from the B plus to the B minus, which is what you'd expect, and that's kind of like any DC bus bar you have flowing to your chassis ground. Whatever your component is that's connected, you connect it to the bus bar on the positive side and the ground on the negative side, and then current flows through. But look, on step 3, what we have is that the B plus, which is here, is ground, or low, and the B minus, which is here, is positive, and it's high. So what that means is that in step 1, we're flowing current in here, along here, and down here. Whereas in step 3, we're actually flowing it the other way. So we're going in through B minus, through the coil, and then out to B plus. Or if you've got the 5-wire, it goes either initially that way or then that way, depending on how you energize it. That's a slightly different way that it's coded for the 5-wire. But the point still stands that even though these are labelled as positive, positive, negative, and negative, that's not actually what's always happening with them, and these are just arbitrary labels, and as long as you match this all up to your code, it'll work fine. So, one way that we can think of this is using the right-hand curl rule, and that says that if your thumb is pointing in the direction of the current flow, your hand curls around in the direction of the magnetic field. So in step 1, where we're flowing from plus to minus, we're flowing that way and the current goes that way. And then in step 3, we're flowing into B minus and out of B plus, so we're going that way and the coil goes the magnetic field goes that way. So we've now reversed the direction of the current. Yeah, current and field. So what that means is that in our usual wiring, where this happens when we run the stepper motor, well, what happens if we... Let's just turn the power off while we do it. What we'll do is that we'll swap this over. So this is coil A in this case, and we'll loosen you off, and we'll loosen you off, and then we'll swap them over. And here's where I find they won't quite go in properly because I haven't quite loosened it off enough. If not, we're going to have to get the impact on you. We're in. And for the win. Fasten-y, fasten-y. Tighty, tighty. And you're in. But even better, you know that you're right when you can predict something. So if we look at this, here's a visual representation of how the field flows from this energizing, energizing table, if you will. Now, if you've read a book on electromagnetism, you will know what these symbols mean. And this is a magnetic field that's coming out of the page, going into the page, and the dots are coming out of the page. It's almost like looking at an arrow from a bow and arrow, where here you're looking at the point of it coming towards you, and here you're looking at the tail of it going into the page away from you. So what we can see is that when we energize and we do this, A plus is positive and A minus is ground, and B plus is positive and B minus is ground. Well, what we have there is the current is flowing from the positive side to the negative, or the positive side to the negative side of the coil. And we're saying, just in this instance, that this is corresponding to a field going into the page and into the page. Because we're saying when positive is positive, we're flowing in, and when negative is positive and positive is negative, we're flowing out of the page. So then what happens on step 2? Well, step 2, we have got that A plus is ground and A minus is positive, so we're coming out of the page. And B plus is still positive and B minus is still ground, so we're flowing into the page. Step 3, we've then got A plus is ground and A minus is positive, coming out of the page again. And then B plus this time is also ground and B minus is positive, coming out of the page. And then the same thing for step 4 here. We've got A plus is positive and A minus is ground, out of the page. B plus is ground and B minus is positive, coming out of the page. Sorry, that was into the page. Can't remember now. Either way, we have this step sequence here where the field in both the windings, to say completely arbitrary and named however you like, is flowing in this direction, or this directional sequence, as you reverse the current flow back and forth by writing the different inputs and outputs high and low. So that means that if we say that this is step 0, and this is step 1, and this is step 2, and this is step 3, well, we have reversed... Okay, what we've done here is actually we've reversed A, because we reversed these ones and swapped them over. So what we can say now is that A is now coming out of the page while B goes into the page, and that is step 1. And then we've got A and B both going into the page, which is step 0. And then A out of the page, B into the page, which is step 3. And then both coming out of the page, which is step 2. So what we have here in the correct usual wiring is that our sequence goes 1, 2, 3 and repeats. But here, we're going this way now. We're going 0, 3, 2, 1. So what we're going to find is much like reversing the cables on or swapping 2 cables on a 3-phase motor. This stepper motor is now going to go the other way because we've got the polarity different on this. Or it's not even the polarity, it's the fact that we're writing the windings, or we're writing certain outputs high, which is going to affect which way the current flows through it. So when we now turn the power back on and we'll reset the program here, what we're going to find, if we've predicted this correctly, is that we're now going to run backwards because we've got the A winding wired backwards, if you will. So remember, we went clockwise before here, and now we're predicting this, and we're going to go anti-clockwise. And there we go, we've gone anti-clockwise. So what happens now, hello, it's Keen, is if we swap the B one as well, we're going to end up with this, which is actually just the same as this, the normal wiring, but just out of sync, or the step starts at a different position. But then the order will still be 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Even though we've actually got both coils at this point wired backwards. Assuming polarity is actually a thing and required. Well, it is sort of required, but whether or not it's arbitrary or not is a different question. The answer is, of course, yes it is, which we can see from the step sequence and what we're witnessing doing this. On you go. So now we have got both coils wired backwards. We could change this in code, but it doesn't drive it home quite as easily because it's not a physical thing, but you've watched me change the cables and not change the code. So you might believe it. So now we've got both coils backwards. So we think we're going to get the same as this. Just we're actually starting here and then going to there and then repeating. So instead of going 0, 1, 2, 3, we're now going 2, 3, 0, 1. So reset and this should go clockwise. And it does. So, for completeness, we'll now put A back to the correct way round. And then we're going to be in this situation, which is the same as this, just again it's halfway out of phase with it. In the sense that we're just starting at a different point in the cycle, but the actual cycle is still going to be 0, 3, 2, 1, 0, 3, 2, 1. Oh no, yeah, these ones don't go fully in. So, tighten, tighten. Back on and reset, and now we're going to go anti-clockwise, which it does, because now we've just got the one coil reversed. So now, for completeness, we'll put it back to both the right way round, and we're going to run it again, and it's going to go clockwise, because now we've gone full circle. So it's going to go clockwise. And it does. So does polarity matter on your stepper motor? And the answer is yes, it does. but at the same time it is also arbitrary, and as long as you're entirely consistent, it really doesn't matter how you wire it, as long as you end up with either the right sequence. So if you do get it wrong, swap the wires over, change your code over, whatever you want to do, but you will always get the same equivalent when you basically follow through what the field's doing in the windings like that, which is most useful for these 4-wire stepper motors. And it does get a little bit different if you've got a 5-wire, 6-wire, 7, 8-wire, and so on. But for your 4-wire, you're all right. But yeah, polarity does affect it, but it is also arbitrary. So the answer is it half affects it, right? Anyway, that's all she wrote.